This video is about being able to use the trapezium rule to approximate the area under a curve. So some functions cannot be integrated easily or cannot be integrated at all. So we need to find another way to find the area under the curve. So what we do is we use the trapezium rule to estimate the area under the curve. So just remember, the trapezium rule gives you an estimate. So imagine we're trying to estimate the integral of y dx between a and b. So that means if this is a function y is equal to f of x, then we're trying to find the area under the curve between x equals a and x equals b, which is this. Okay, and what we do is we divide the area up into n equal strips. So this is strip 1, strip 2, strip 3, blah, 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 all the way up to strip n. So we have n strips. Then that means the width is equal to b minus a, because obviously the whole length is b take away a. So all this is b take away a. And because we divided it into n strips, then the width of each one, so this is important, the width h is equal to b minus a divided by the number of strips, which is n. Okay, so b is upper limit, a is a lower limit, n is the number of strips. Next, we calculate the value of y for each value of x that forms a boundary of one of the strips. So that means if this is a, then that y value, corresponding value at a is y0. Okay, similarly, the next one will be y1. This one will be y2, so on, all the way up to yn minus 1, and the last one, which is there, which is y sub n. So let me just write this one properly. Yn minus 1. Finally, what we can do is if we just draw a trapezium, so join up y0 to y1, y1 to y2, y2 to y3, so on, then what we do end up getting is a series of trapeziums, and all we need to do is work out the area of each trapezium and add it together to get an estimate for the area under the curve. Okay, so if I were to sketch out the first one, so using GCSE knowledge, so my first trapezium looks like this. So I know this is y0, and the height here is y1. And I know this is h, because we work, which is b minus a divided by n. Then area of a trapezium formula is half a plus b times h, where a and b are parallel. Now the parallel ones are obviously y0 and y1. So it's going to be half of y0 plus y1 times height, which is labeled as h here. In a similar way, we can find every single trapezium. So when we add it up, so the area is approximately, area, which is the integral from b to a y dx. Now, because we're using an approximation, because we obviously divide it into trapezium and it's not exactly the area, this is approximately equal to the first trapezium. Now, the area of the first trapezium is half of y0 plus y1 times h. The next one would be half of y1 plus y2 times h. So this trapezium. Okay, and the next one would be half of y2 plus y3 times h. Plus dot, 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 all the way up to half of yn minus 1 plus yn times h. So all we've done is we've summed up all the trapezium, area of the trapeziums. Now what you can see is that this is approximately, obviously, still equal to, there's a common factor of half h here. So I can collect the half h outside, factorize it out. And inside the square bracket, I'm going to get y0 plus y1 from the first bracket, plus y1 plus y2 from the second bracket, plus y2 plus y3 from the third bracket, all the way up to the one previous to this will be yn minus 2 plus yn minus 1. And the last one will be yn minus 1 plus yn. Now what you can see is, you can obviously see there's two lots of y1, two lots of y2, two lots of y3. Everything there will be two lots of. The only one there won't be two lots of is the first one, which is y0, and the last one, which is yn. So this is approximately equal to half h y0 plus two lots of y1 plus y2 plus dot 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 yn minus 1. Oops. Rounded bracket. Plus yn. And that is the formula, trapezium rule, for area under curve, for approximating an area under curve. So just be careful here. A thing to note is there is always n plus 1 y values. Because remember, there's the y0 and then all the way up to yn. So there's n plus 1 y values. So this is the formula that you need to remember. Where h is equal to b minus a over n, where n is equal to number of strips. So area. So this is the approximation that you use to find the area under a curve where you cannot integrate the function. Okay, let's go through it via an example. Okay, use the trapezium rule with 4 strips to estimate the area under the curve with equation y is equal to root 2x plus 3 between the lines x equals 0 and x equals 2. Okay, a thing to note is this formula is available for you in the formula booklet, so you do not need to memorize it. So in this question, the number of strips is equal to 4, so n is equal to 4. My a is equal to, my b is equal to 2, and my a is equal to 0. So that means h, which is equal to b minus a over n, will be equal to 2 minus 0 over 4, which is equal to 0.5. Okay, 0.5. That means I need to substitute into my function, so x and y. I need to substitute into my function starting from 0, because my a is 0. I need to go up in 0.5, because my h is 0.5. So 0.5. Next one would be 1. Next one would be 1.5. And the last one would be 2, because b is 2. You can see I get 1, 2, 3, 4, 5 values, which is 1 more than the number of strips that I have. And then I need to substitute these values one by one into my function. Now, the easier way to do this is if you, in your calculator, you go to menu, then you press 9 for table, because this will give you the table function. Then you input f of x, and then press equal after you input it. Then you need to ignore, so do not input g of x, just press equals, because you don't have a second function. Okay, the next thing you need to do is, after you press equals, is you're going to get a list. So it says start, end, and then steps. Okay, so you need to start at, because a is 0, you need to start at 0. You need to end at 2, and you need to go in steps of 0.5. So you need to input this. So 0, 2, and 0.5 from here. Okay, when you substitute these values in, so when x equals 0 into your function, the table function does this for you automatically. For the first value, you get 1.732 to 3 decimal places. For 0.5, when you substitute 0.5 into the function, you get 2. When you substitute 1 in, you get 2.236. When you substitute 1.5 in, you get 2.449. And when you substitute 2 in, you get 2.646. So the area, so when you integrating between 2 and 0, root of 2x plus 3 dx is approximately equal to half times h, so half times 0.5 times, okay, the first value comes up once, which is 1.732, plus 2 lots of 2 plus 2.2 plus 2.236 plus 2.449 plus the last term on its own, 2.646. Let me just separate this out. Okay, when you put this into the square brackets into your calculator, you get half times 0.5 times 17.748, which is equal to 4.437. So that will be your answer. Just a word of warning at here, the formula is written y0 plus yn plus 2 lots of everything in the middle. When I've input into my obviously example, I've done y0 plus 2 lots of everything plus the last term. So I've just rearranged it, but it's still the same answer. Okay, let's look at another example. So it says, use the trapezium rule with n strips to estimate the integral between 2 to 0 of root x dx in the cases, or in just the case n equals 6 and to 3 significant figures. Okay, so so I've got my a in this case is 0, my b is equal to 2, and my n is equal to 6. So my h is equal to 2 minus 0 divided by 6, which is equal to a third. Okay, so I need to substitute into my function for my x values of 0, a third, 2/3, 1, 2/3, which is just 4/3, 5/3, all the way up to 2. So I should have 1, 2, 3, 4, 5, 6, 7 values, y values, which is right because my number of strips is 6 and my number of y values has to be 1 more. So when I use my table function in my calculator to substitute these values in, I get 0 for the first one, 0.577 for my second one, 0.816 when I substitute 2/3 in, 1 when I substitute 1 in, 1.155 when I substitute 4/3 in, 1.291 when I substitute 5/3 in, and 1.414. Okay, so I need to do, obviously I'm integrating between 2 and 0. Root x dx is the same thing, well, approximately equal to half times my h, which is a third, times by first y value plus last y value plus 2 lots of everything in the middle. So 0.577 plus 0.816 plus 1 plus 1.155 plus 1.291. Okay, where I substitute everything in my square brackets into the calculator, I end up getting 11.092. When I do half times a third times 11.092, I get 1.8487. I want to round it to 3 significant figures, which is roughly going to be equal to 1.85. So that was my answer for A. Okay, compare your answer from part A with the exact value of the integral and calculate the percentage error in each case. Okay, so if I'm trying to work out the exact value, I need to do a definite integral. So root x dx is the same thing as in index form x to the power half dx. When I integrate x to the power of half dx, I get x to the power of 3/2 divided by 3/2, which is the same thing as multiplying by 2/3. Okay, so I need to substitute 2 and then substitute 0 in and subtract it. So 2/3 times 2 to the power of 3/2. When I substitute 0 in, I realize I get 0, so I just get 0. Okay, if I put that into my calculator, 2/3 to the, times 2 to the power of 3/2, I get roughly 1.8856188083. Okay, so if I want to now work out the percentage error is equal to actual takeaway estimate divide by actual times by 100. So in this case, my actual is 1.8856, blah, blah, blah. Take away 1.8487. I'm just going to use a non-rounded version. All over 1.8856, blah, 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 times by 100, which gives me 1.95787. And if I round it to three significant figures, I get 1.96%. So that would be my answer for percentage error. So when is our approximation an overestimate or an underestimate? So there are two different cases we need to consider. So when our function goes like this, or when our function goes like this. So if we were to split it up into trapeziums, what you realize is your trapeziums are below the curve for this one. And when you split these ones up, this functions that look like this up, you realize your trapezium is slightly above because your curve is curving downwards, yeah? So for these ones, you have the curves. For these functions that looks like this, the curve lies above upper edges of each trapezium. Therefore, it's a estimate. Okay, and this one, the curve lies below upper edges of each trapezium. Therefore, overestimate. So what I would do in each example is sketch out my function, or if the function is drawn for you, and then check whether when you split it up, your trapeziums, the edge of your trapezium lays above or below the curve. Use the trapezium rule to obtain approximate answers to three decimal places for the following integrals. Okay, so for this one, question 1, let's do it here. Okay, your A is 2 and your B, so A is 0, B is 2, your N is 4. So which means your H is equal to 2 minus 0 divided by 4, which is a half. So when you're substituting your X and Y values in, you're starting from 0 going up in halves. So half, 1, 1.5, and 2. So use your table function to substitute into the function 1 over 1 plus x squared in steps of half from 0 to 2. So when you substitute these values in, you get 1 when x is 0, 0.8 when x is a half, 0.5 when x is 1, 0.3077. Now because I want the answer to 3 decimal places, I'm going to round my answers to 4 decimal places, so 1 extra. And when I substitute 2 in, I get 0.2. So the area, when we integrate 1 over 1 plus x squared dx, is roughly equal to half times h, which is half again, times by first y value 1 plus last y value 0.2 plus 2 lots of everything in the middle, 0.8 plus 0.5 plus 0.3077, which is equal to, if you put into a calculator, it's half times everything in the square bracket equals 4.4154. When you do half times 4.4154, you get 1.10385. And if we want to round it to 3 decimal places, it's 1.104. Okay, if I want to do part 2 now. Okay, so my A in this case is 0, my B in this case is 3, my N is equal to 3, h is equal to b minus a over n, which is 3 minus 0 over 3, which is equal to 1. So that means when I'm substituting my x values in, I need to start from 0, go up in ones, all the way up to 3. Okay, and when I substitute 0 into root of 1 plus x squared, I get 1. When I substitute 1 in, I get 1.4142. Again, I'm rounding to 4 decimal places because I want my final answer to correct to 3 decimal places. 2 is 2.2361. And when I substitute 3 in, I get 3.1623. So the integral of 3 to 0 of root 1 plus x squared dx is approximately equal to half times h, which is just 1, times first value plus the last value, plus 2 lots of everything in the middle, which is 1.4142 plus 2.2361. Half times 1 times everything in the square bracket equals 11.4629, which if I do half times 1 times 11.4629, I get 5.73145, which is approximately, to 3 decimal places, 5.731. Okay, next question. Use the trapezium rule with 5 scoops. Find an approximate value to 4 decimal places for 1 plus x squared to the power of 12 integrated between 0 and 0.5. So my a in this case is 0, my b is equal to 0.5, my n is equal to 5, h is equal to b minus a over n, which is 0.5 minus 0 over 5, which is 0.1. So my x values start from 0 and go up in 0.1s, all the way up to 0.5. Okay, now I need to substitute these x values into my function, which is 1 plus x squared to the power of 12. So I substitute 0 in, I get 1. Now I want the final answer to be to 4 decimal places. So when I'm rounding these answers, I need to do it to 5 decimal places. Make sure you hover in your calculator, you hover on the y value, and then it'll give you the non-rounded answer. And then round it to 5 decimal places. So 1.12683. When I substitute 0.2 in, I get 1.60103. When I substitute 0.3 in, I get 2.81266. When I substitute 0.4 in, I get 5.93603. And then when I substitute 0.5 in, I get 14.55192. So when I'm integrating between 0.5 and 0, 1 plus x squared to the power of 12 dx is approximately equal to half times h, which is 0.1, times first y value plus last y value plus 2 lots of everything in the middle, which is 1.12 lots of 1.12683 plus 1.60103 plus 2.81266 plus 5.93603. I put everything in the square bracket into the calculator. I get 38.50502. If I do half times 0.1 times 38.50502, I end up getting 1.925251, and I want this to 4 decimal places, so this is approximately 1.9253. Okay, one last question that I'm going to go through. Use the trapezium rule with 2 strips for each of width 4 to show that an approximate value of 9 to 1 integral of 4 root x dx is 32 plus 16 root 5. Okay, so in this case, 1, my A is equal to 1, my B is equal to 9, my N is equal to 4. So N is equal to 2. So H is equal to B minus A over N, which is equal to 9 minus 1 divided by 2, which is 4, which we had there anyway, so 4. That means my in my table of value, my first value is 1, x value. 1 plus 4 is 5, next x value is 5, and the next value, x value, will be 9. So I get 3 y values, which you do get with 2 strips, okay? So now, because I'm trying to find the answer, I'm going to just substitute into my function, which is 4 root x. So for this one, it'd be 4 times root 1, which is just 4. Okay, this one would be 4 times root 5, which cannot be simplified, so it's 4 root 5. And the last one will be 4 root 9, which is 4 times 3, which is equal to 12. Okay, which means the integral between 9 and 1 of 4 root x dx is approximately half times h, which is just 4, times first plus last value, which is 4 plus 12, plus 2 lots of the one in the middle, which is 2 lots of 4 root 5. Okay, half times 4 gives me 2. 4 plus 12 is 16. 2 lots of 4 root 5 is just 8 root 5. Which is gives me, if I multiply out the 2, I get 32 plus 16 root 5, which is what I was trying to find. Okay, part 2. Use a sketch graph to explain why the actual value of 9 to 1 4 root x dx is greater than 32 plus root 5. So I know, so if this is my axis, is x and this is y, then root x looks like a curve, but 4 times root x is just a stretch, so it's just going to be like this. So this is y is equal to 4 root x. So if I split it up into 2 strips between a and b, let's just say there to there, then you can see clearly my trapeziums are below the curve. So curves are above the upper edge of each trapezium. Therefore, is it underestimation? Underestimation. Therefore, actual value is greater than 32 plus 16 root 5. And the only thing that I would say is, if I were to do it correctly, I should have done it between 9 and 1. So when I did split it up, I should have split it up like this. It's still an underestimation, yeah? Okay, part 3. It says, use integration to find the exact value of 4 root x dx between 9 and 1. So 9 and 1, 4 root x dx is 9 root 1, so 9 1, 4 times 4x to the power of a half dx. So when we integrate this, we get x to the power of 3 over 2, and we get 4 divided by the increase, which is 3 over 2. Let's not do too many things at once, between 9 and 1. Let's simplify it now. So I end up getting 4 times 2 divided by 3, which is 8 over 3. X to the power of 3 over 2 between 9 and 1. Now I need to just substitute in. So 8 over 3 times 9 to the power of 3 over 2. Take away 8 over 3. Don't like that 8. Times 1 to the power of 3 over 2. Which gives you, for the first value, you get 72. And if you put that into your calculator, for the second value, you just get 72 minus 8 over 3. If you put that into your calculator, you end up getting 208 over 3.